I will begin with a word of prayer. Eventually. Heavenly Father, we thank you for this day. Again, I thank you for this class and this opportunity we have to meet and study electrodynamics and potentials of time-varying field, potentials rather, sources. Anyway, you know what I'm trying to say, thankfully. We just pray that you be glorified in what we do, Lord. In your name I pray, Lord Jesus. Amen. Amen. It's very good the Holy Spirit can understand like what we're trying to pray and put the words together that we can't put together, because some days that's like really important, like every day. So last time we looked at the retarded potentials, and they're actually really smart, as it turns out. And so we showed that the retarded potentials solved the inhomogeneous wave equation, which the inhomogeneous wave equation for the potential, I mean, we didn't show all of that, right? Truth be told. So we worked out that Ampere's law and Gauss's law are basically interchangeable with Mach squared times the potential is minus 1 over epsilon naught the density, and Mach squared on the vector potential is minus mu naught times the current density, right? So that's the first thing we did last class. We showed that those equations are, equivalent, if you will, to the inhomogeneous wave equation, so-called. And we also had that we're going to formulate the electric field as minus the gradient of V minus partial A partial T, and the magnetic field is the curl of the vector potential. All right? And so we've also discussed that those are essentially interchangeable with, we've got Faraday's law, right? And no magnetic monopoles, right? Like this formulation automatically gets you these two, right? But then if we have sources, we need to solve those inhomogeneous wave equations. And what we showed last time was that if you define the retarded time as, T sub r is equal to T minus, I hate the symbol, script r over C. I could kind of write it on paper, but on the whiteboard it's much more challenging for some reason. So separation distance divided by C. Then we can write down the retarded potentials, Vt 1 over 4 pi epsilon naught, again the very smart retarded potentials, integral of, I will not tire of this joke, rho of r prime tr, I endeavor to be worse, script r, my politics, d tau prime, some of you know, others of you haven't left well anyway, all right, mu naught over 4 pi integral of j at r prime comma. So we're integrating the charge density. Work. These are the retarded potentials, all right? And so essentially what's going on is we're saying that the voltage and the vector potential at time t is caused, right, by what happened in terms of the charge distributions and the current distributions at the time before time t. How much time before? Well, however much time it takes for a signal to go from the speed of light at the source to the field point, right? That's what this is. It's assuming, it's building in this speed of light travel of information about the change, like the changing source, excuse me, to the field point. Now, so I wanted to show you guys an example, which I don't think we didn't do the example last time, I don't believe, right? No, I don't think so. So we just all we did last time, actually, to be to be fair, and also there was this condition here, right? Lorentz gauge, which was what? How'd that go? I've already forgotten the Lorentz gauge. Oh, sadness. Uno momento, if you please. This is all built over that as well. Okay, so the divergence, the divergence of the vector potential plus u naught epsilon naught partial v partial t, that has to be equals to 0. That right there is the Lorentz gauge condition. And again, the t is not supposed to be there, but I don't care. Sorry, Griffiths and historians who care more. But anyway, whatever. Add the t, don't add the t, I don't, whatever. As I said last time, I feel like this is like the L'Hopital situation. But anyway. So example 1 from last class, actually. We have an infinite straight wire. And we have like I of t equal to 0 for t less than 0 and I sub naught for t greater than 0. All right? So in this situation, we're going to assume so the question is to find the electric and magnetic fields. This is a problem we could not solve before, because we're talking about time-varying current, right? This is new. And so, like pictorially, what should happen, right, is there ought to be some sort of like cylinder, right? At time t. Right, and so like if if we're at like t positive, right? This distance out here would be like ct, right? S equals to ct. That's how far the information about this current, like the current would be, the current goes along here, is what I'm saying. I guess I didn't write that down yet, but z hat, yeah? There we go. So I'm supposing that the current is flowing along the z-axis, right? Like that. But it switches on at time 0. So after time 0, there's this signal spreading at speed of light outward. There's a cylinder in which the news that the current started flowing should be seen. So it's only within this cylinder, this light speed expanding cylinder, right, which the electric and magnetic field should be non-zero. All right? So that's the sort of the big picture of what we should discover as we work this example.
Are we just assuming that like the whole wire is something instantly current?
Yeah, the whole, this is a constant current everywhere. So once it just starts moving everywhere. Yeah. So there's no, that in some sense makes this problem two-dimensional, because it's the same story at every z, right? It's really just, you could look at it in terms of, coming out at you, right? There's some kind of E, B not equal to 0 in here, and out here, E and B got to be 0 because they were 0 to start with, right? And there's that light cylinder. Not a light cone, in this case, a light cylinder. But, well, anyway, maybe it's a light cone still if we were to graph time. But anyway, one kind of physics at a time. Let me alone. Okay, so, great. So we've got V is equal to 0. We'll assume wire is neutral. All right. So that means that we're just responsible for calculating the vector potential. All right. And we're going to calculate the vector potential at the points of interest, right? Which is the ones where, I mean, goodness gracious. All right, so what I'm trying to argue basically is that J of R prime TR is equal to 0, you know, for S greater than CT. Okay, so like there's no calculation to do outside the cylinder, because outside of the cylinder, you know, when we evaluate the source, the current density at that time, it's 0, because that would put the retarded time, I think, would be like less than 0 if we work through it. But all right, that's how it should work out anyway. Okay, so all right. So for time greater than S over C, which is equivalent to saying S is less than CT, right? There's two different ways to look at this, you know? So don't let me confuse myself over that. We have, I'll eventually start the calculation, guys. The vector potential at ST should be equal to mu naught I naught divided by 4 pi z hat times the integral from minus the square root of CT squared minus S squared to the square root of CT squared minus S squared. And then I have dz divided by the square root of S squared plus Z squared. So we're just putting into practice what this is how we'd calculate the current density in this context, right? Because we just have a line current. And this is the part of the current that would be in communication with the point ST. I could draw a picture, I suppose. That might be helpful. All right. So here's the point we're looking at. And we're thinking about this little bit of current, right? It's going upwards. So this is the z-axis, of course, but we're looking at it at position z. This distance here is S, and the distance between the source current and the field point, of course, we call script r. And script r is the square root of S squared plus Z squared here, right? And I guess we should think about the retarded time for a second here. TR is what? It's T minus script R over C, right? So we need TR to be positive for, you know, I of TR to be equal to I naught Z, right? I mean, we could put a vector on it and make it z hat if you like. So you see that in order to have that condition, we need t minus script r over c to be greater than 0, right? Which is to say that we need ct is greater than script r, which, by the way, is equal to the square root of s squared plus z squared. So I think that explains the bounds, right? This is the maximum extent at which we have the non-zero current felt at the field point. Past that, plus or minus, it's outside. It's further than CT away, you know. All right. I got to close this door. It's distracting me somehow. As you guys know, I'm easily distracted. Now, I think we can make this integral easier, right? It's symmetric. We can just double it up, right? So just trade this out for mu naught I naught z hat over 2 pi, integral from 0 to the square root of ct quantity squared minus s squared, and then we got our dz over the square root of s squared plus z squared, which is a known integral, which I'm just going to write down if you guys don't mind. So we got ourselves mu naught I naught z hat over 2 pi times the natural log of the square root of s squared plus z squared plus z, close parentheses here. Evaluate that thing from 0 up to the square root of ct squared minus s squared. And so what that gives us is mu naught I naught over 2 pi times the natural log of the quotient of ct plus the square root of ct quantity squared minus s squared, all divided by s in the z hat direction. All right. And I had this worked out before last class. I just ran out of time. And this morning I thought, oh, I'll just finish this example. It'll take me 10 minutes and I'll be on my merry way. No. It's bad. It's very bad. Like, what comes past this point is very bad. I mean, okay, great. We've got the vector potential. Yay. Woohoo. But what about the fields? Yeah. Yeah. Ooh, indeed. Because now we have the joy of calculating the curl. We'll get there. So the magnetic field is the curl of A, right? And that, if you look at it, is minus partial AS partial S. Well, that's wrong. I think I'm at a Z there. What happened? That's a Z. Because we've only got a Z component, right? So partial A, partial minus partial AZ, partial S, phi hat. This is what we're up against. That's what we actually have to calculate, right? And so I'm going to jump a few steps down, if you guys don't mind. Mu naught I over, let me go, I'm going to go 4 lines down. Maybe you guys can track. Mu naught I naught 2 pi over phi hat. And when you do this differentiation, if I can find a marker that works better, it'd be lovely. All right, we do the differentiation. And what is going to give, what it's going to give us, as you can see, there's like, you know, a lot going on there. So the way I looked at it the first time was I had S divided by CT plus the square root of CT squared minus S squared times 1 over S squared times minus S squared over square root of CT squared minus S squared. Hopefully I haven't skipped lines here. Minus parentheses CT plus the square root of CT squared minus S squared, close parentheses, close other parentheses. Hooray. All right, well, tell you what, let me just save myself a little bit of work here. I'm going to show you on the projector in a second, but after much calculus, this is mu naught I over 2 pi s CT over the square root of CT squared minus S squared times phi hat. It took me about a half hour to get this stupid thing to work, because I worked it. I'll show you in a minute. So it's that. All right. Not obvious, not at all obvious. Okay, like I will show you the rest of the. I'm gonna project the rest of the calculus here in a minute. We'll actually work out the electric field, though. I'll do that one entirely on the board if that's okay with you guys. The magnetic field is. I mean, they're both about the same badness, but. All right, I think I'm going to erase the blue and do it there. Steal it from the Lorentz gauge. Like I can calculate the. Well, but I'd still have to do. I'd have to integrate though, wouldn't I? Oh, the electric field. Oof. No. I don't know. No, Sam, no. Just because there's an equation that connects V and A doesn't mean that you necessarily should use it that way, especially when there's a derivative involved. And if you look at it, the electric, well, anyway, oh, okay, I kind of see why you're saying that, but there's a slight structural difference. Oh, I erased the thing I needed, but we'll write it down again here. So the electric field is minus partial A, partial T, right? But that's minus partial T of the A, but the A, let me write it out this way. It's mu naught I naught over 2 pi. And I think it's best to look at the natural log of a difference rather than a quotient, because then the calculus is a little bit more manageable in my view. I mean, this is particularly nice. Part of this, what I'm about to write down, is very nice. What happens to that S term there? V is 0. Yeah, right? Yeah. But so is this, because we're doing time derivative. And, all right, but then there's this, which is unpleasant but manageable. So we've got minus mu naught I naught. I'll put the z hat out front, why not, over 2 pi. All right. Differentiating this gives me 1 over CT plus the square root of CT quantity squared minus S squared right? Then chain rule says multiply that by c plus square root differentiates to c squared, well, I think 2c squared t divided by 2 square root of ct quantity squared minus s squared, like so. Notice the 2's be canceling. Get rid of them. If you're wondering about the c squared, notice that ct squared is c squared t squared. So when I differentiate that with respect to t, you got a c squared. You definitely need that c squared there, right? So then, make a common denominator of this brackety thing here. Minus mu naught I naught z hat divided by 2 pi 1 over a ct plus the square root of ct squared minus s squared, right? All right, then common denominatoring this thing. Pull a c out, by the way. I think I want to factor a c. Yeah. Factor a c out of this thing. Yeah. There it is. Now that's a 1. So I've just got a square root of ct quantity squared minus s squared plus ct divided by the square root of ct quantity squared minus s squared. Close the bracket. Close the other bracket. Oh. And now you can see what remained hidden from me for at least a half hour this morning. Not in this one. It's somehow worse in the curl. Curl's always worse. But that, be canceling that. Yay. And so what we're left with is simply minus mu naught I naught c divided by 2 pi times the square root of ct quantity squared minus s squared z hat. So there you go. That's the electric field at st, at the points where it's non-zero inside the cylinder of propagation. So the electric field is in the z direction, but downward. Yeah. The magnetic field, on the other hand, we found was what? Mu naught I naught over 2 pi s, right? And I'll show you the details here in a minute, but square root of c squared, well, ct squared minus s squared phi hat. Right? So there's the magnetic field inside the cylinder of non-zero fields. Does this make sense? These formulas, do they make sense to you guys? So what happens as t goes to infinity? What happens? Yep, we find E goes to 0 and B goes to what? See, this thing limits to 1, right? And so B just goes to, yeah, what did you say, mu naught I naught over 2 pi? Well, it has to, right? The magnetic field of a long steady current. And so the further you get away from the initial ripple of turning it on, the more it looks like the steady state actually. This factor becomes closer and closer to the one the further you get away from the wire when it, in terms of the time it turned on, like traveling away from it. So.
But B starts out lower than E, right?
Yeah, B starts out at 0, it's true. Yeah. B does start out at 0, whereas E starts out at, ooh.
Depends where your S is.
Well. Yeah. All right. You got to know when you're beat. It is time for us to. I will show you all the things I did not write out just now. What's that?
Does E just start out at infinity?
It seems like that can't be right. I think that, well, okay, so you shouldn't ask the question what happens at S equals to 0 anyway, right? Like the field should not be defined where the current's flowing. So we have to think about like a finite S, and I think it's, I don't know, I'm not sure.
Well, when you turn it on, that's the only place it has influence. Is at 0.
Yeah, well, I've covered up the formula, but
The moment you turn on, it's back to 0.
What I mean is that, like, when you look at retarded time and you get a 0 minute.
yeah, I'm not sure what we should say at the actual retarded time. Like, you're asking the question, what happens on the cylinder? I'm not sure at the moment. That's a good question. That is like a fundamental question to ask that I just haven't processed yet. I thought about it, but I don't have an answer to that. So I've been trying to not say anything about it. So you got me. Could I animate it? Well, get my tech guy to. All right.
Just write it out in your mind. Yeah. Just run some numbers.
I've almost got it, guys. I've almost got it. All right. I got it. Here we go. Okay, so, and I will eventually catch up on my note posting. I'm sorry, I'm quite far behind at the moment, but I have not forgotten. I just need to find 30 minutes to post them. So, all right. So we did this bit, right? And then I wrote it like that. And here's my first attempt. So when you look at, at the start, I'm writing all kinds of details out. Check it out. The phi component 0, the S component 0. So the Z is all that survives. And there's just two derivatives involving the Z component of the, the curl and cylindrical coordinates. There is no phi dependence, that's gone. So that's all we have to deal with. That's it. So that means we're differentiating this, which I put this one first, 1 over S, and then this is the chain rule, right? And then I factored an S out because I saw Griffiths had an answer out here with an S. I'm sure that just must all fall into place, right? No, it doesn't. So then you have this, and you start to think, did I make a mistake? This doesn't feel right. And then I made a common denominator, and then it didn't make it feel better. I didn't feel better at this point. I didn't feel better at all. And then I simplified it, and I looked at it, and I said, well, that's great. Wonderful. Like, oh, okay, well, what am I supposed to do with that? And at this point, I was like, yeah, I'll try it again. So this is actually from later. So then I decided to try to do the differentiation a different way. at which point I became more careless and wrote A sub s rather than A sub z, which is really what I was doing. And I decided that it'll be better if I make a u to guide my work. So I invented the letter u, which is this thing. So 1 over u times the partial of u, that's the chain rule, right? Okay, didn't make a mistake there yet. Then I differentiated it. And then I had this nagging feeling like it's just taking me back to where I just was a second ago. I did the quotient rule this time around because that's how it came to me. So I did the quotient rule. That brought me to the step that I just wrote down on the board over here. After the quotient rule, I got this. Kept my 1 over s squared there, and this is the u, and I don't know where this s came from. I guess someplace. Whatever. Anyway, so it's correct. I'm pretty sure, or at least I've made an even number of errors. So all right, great. So then after a bit, I got to this, and then I made a common denominator. And then at the end of this, all of a sudden it hits me, I'm right back where I got to the last way. You know, because this actually is where I got to on the previous page. I'm like, at this point, I realized, oh, I can factor a square root of this from here. See, there's CT worth of it over here. And there is a square root of it over here. And then, look at that. This and that be canceling, which is the same cancellation we saw in the electric field calculation, but it's a little bit easier to see there, which just left us with the formula I wrote down. So yeah, seems like whenever I don't quite get to an example at the end of class, and I think it's a simple example, like there's something horrible waiting for me in the details, because this like ate an hour today, and I mean I think it's. I had to show it to you because it took me an hour, right? Otherwise, it would just feel like it was a waste of time. But now I've showed you, so you will be spared that hour, perhaps. I mean, that hour is good, though. You learn something from it. I'm not sure I'm learning anything from it. You guys would learn something from it, maybe. Here's the calculation of the electric field we just went through. And finally, yay, it agrees in the limit in the sense that we'd like. So that's that. So we move on to the next bit. This is lecture 33, which is on Jefimenko's equations and the Lienard-Wiechert potentials, which I'm probably saying both of wrong. I don't care. I mean, I care a little bit, but I've got no one to correct me, so what can I do? Oh, yeah, Budaras will correct me. I said Aharonov bomb effect wrong. He's like, you mean Aharonov? Or I forget what he said. He corrected me, but you know how he is. Correct and stuff. But anyway, cultured, that kind of thing. Let's see here. Anyway, so as I mentioned last class, namely this class, if we, last class I mentioned that if you plug the retarded time into the formulas for Coulomb's law and the Biot-Savart law, they don't work. All right, Jefimenko's equations answers the question, how far off are they? See, because what Jefimenko's equations are simply taking the retarded potentials and just calculating the electric and magnetic fields that result at this level of notation. All right, so if you go back to the calculation we did last class, which I have fortunately up, look at page 6 here. Remember this stuff we did? We calculated the gradient of V. So we worked this out last class, but like the gradient of the retarded potential, it works out to this. We're going to use that in the Jefimenko equation derivation in just a second here. Let me go back. So try to take a snapshot of that. So to calculate the electric field, I need, the gradient of that, which we talked about last class, and I also need minus partial A partial t. Now partial A partial t is simpler because that just ends up being the integral of the time derivative of the current density. All right, and as such, you've got 3 terms. This is the electric field. This is Jefimenko's equation for the electric field. So like here, without this would be the naive thing to try. This would be Coulomb's law built with retarded time. But it turns out that's not quite right, because there's actually this and that need to be added as correction terms. All right? And when you go through the corresponding calculation, which I have not, full disclosure, I just have not had time to, I don't think it's much different. But I think it also probably impacts the part of last class's derivation that I didn't do, namely showing that we satisfy the inhomogeneous wave equation for the vector potential. Right? I need to work that out for myself. Maybe for you guys, we'll see what happens. But here it is, what you get for the Biot. So like the Biot-Savart law would just be, get rid of this, just that and that would be Biot-Savart retarded time. This is the correction to that. These are Jefimenko's equations. And Griffiths indicates that they're relatively recently discovered, like in the 60s or something. There is a very interesting homework problem, which I may or may not have assigned. I really should have if I didn't, which it explains, like basically, we did this thing before where we, the quasi-static approximation, right, where we pretended like we had static sources even though they weren't, you know? And so we can make precise the abuse of the quasi-static approximation in view of these equations. And so like this problem, it concerns studying how wrong the quasi-static approximation is in view of these correct formulas. And it basically, he argues that there's a really special, like really fortunate cancellation that happens there that makes the quasi-static approximation better than it ought to be. So like it's actually better than you would think. All right, so that brings us to the Lienard-Wiechert potentials. So our formulation of retarded potentials was for a continuous distribution of charge and current, and now we're turning to the problem of a point charge. The question then is, what's the electric and magnetic fields of a moving point charge? This we don't know, right? We have formulas for the force on a point charge before, right? The Lorentz force law, QV, Q times E plus V cross B, right? We know that. But we never answered the question of what's the electric field and magnetic field generated by a moving charge. That has never been answered in your treatment of electromagnetism up till now. We've judiciously avoided that question in both classes. All right. So the Lienard-Wiechert potentials are basically fleshing out what the retarded potentials look like for a point charge. That's what's going on here. So the setup is to let W of t be the position of the point charge Q at time t. That's the notation. We're using W for the position. And so naively, you might expect that your, retarded potential would just work out like that, right? You might expect it would work out like that. And it does not. Sadly, it's not that. And Griffiths has a page and a half where he explains this, and honestly, guys, I don't quite understand at the moment. I'll give you the short version of it. Basically, he says the problem is that if you integrate over the charge density at retarded time, you don't get Q for subtle reasons. The Q moves around, the integral may not give Q, basically. And he gives this argument that concerns sort of like, it's kind of like a Doppler effect kind of argument, but the long and short of it is that you end up having to divide the volume by this factor in order to compensate for the moving, and this velocity, if you're wondering what it is, it's the velocity at the retarded time of the position of Q. That's what the V is. And how do you define the retarded time? Well, the retarded time is defined by this equation right here. So it's the field point we're interested in calculating the potential at, minus the position of the charge at the retarded time, is going to be equal to C times the difference between the time we're measuring the potential at the field point and the retarded time, whatever that. So this implicitly defines retarded time. We have to work out this equation. We will work out this equation for an example at the end of this class. it's horrible. That's actually a lot of the badness. And here's a picture of what's going on. So like, we're asking the question, what's the potential here, right? And we've got this trajectory of Q, it's moving around. And so we've got the, the position at retarded time, and here's it took to get from here to here at light speed is what happened, right? We have a light speed in the separation. Think of it that way. Now, here's a bigger picture of the same thing, yay. So one of the things he points out is that there's at most one point on the trajectory of Q which is in communication with the field point at a given time. And so like, suppose there were 2 points, right? You'd have R1 is C times, T minus T1, and it's also C T minus T2, where these are the 2 different times of the trajectory that both met the same event to measure the field, like the same RT. So the R1 and the R2 are both measured with respect to the same field point. So, but we're saying, suppose there's one field point, there's 2 different points on the trajectory that meet at that same time. If you solve this for the average velocity between those 2 points on the trajectory, you get that the average velocity is c, which is impossible. Like, no charge can move at the speed of light. You may not know this, but it's true. Things that move at the speed of light, and other bosons, neutral particles actually. So certainly light is not charged anyway, and we're talking about electromagnetism, which is about light. So now, so that means that, and he says consequently, that brings us to this equation. This is the retarded potential for a point charge. So we have Q times the speed of light divided by the separation distance times C minus R dot the V, where the velocity is the velocity at retarded time. This is one of the Lienard-Wiechert potentials. And then, since the current density is just density times the velocity, that gives us this here. Now this part of his derivation is he points out that you can pull the separation distance outside of the integral for a point charge. Most of what he's fussing about in the derivation is just understanding this integral, all right? But anyway, again, I don't entirely understand his derivation yet. I'm not saying it's bad, I'm just saying I'm dumb. So anyway, details I don't understand aside, that brings us to, I mean, this I understand. If I have the V, I get the A that I get, because it's the same thing that we just worked through times the velocity. And yeah, so this is the vector potential for a point charge that's possibly moving. All right? What's the simplest possible example you could work out for a point charge? What would be the simplest possible motion that's not entirely stupid? Linear, right? Yeah, constant velocity motion, right? Start at the origin. Seems like a good idea. Let's see how bad that is. Here you go. So we'll assume the position is TV. What's the retarded time? Right? How bad could that be? Well, we are doing this for arbitrary velocity. I suppose the simpler thing to do would be to actually pick a specific, direction for your velocity, but we're not doing that. We are going to suffer through arbitrary direction for the velocity. And when you do that, we square the distance equation, right? And then I FOIL out the thing, and lo and behold, a quadratic equation in retarded time. And so the retarded quadratic equation is right here. As you can see, A, B, and C are not retarded. They just involve the other constants, right? So, yeah, and then I don't really use it that often, but I will used the quadratic formula this once. Don't tell my differential equations class. I'm pretty dogmatic about completing the square in there, you know. Yeah, so that gives you this. And then you got the plus or the minus here. All right, great. I think I canceled a 2 out, right? You notice that there's a 2 here, and there's a 4 here and here. So this can there's a net 2, and that the 2's be canceling. All right, and then Griffiths suggests if we look at the v equals to, velocity going to 0 limit, you can fix the sign there, because if the velocity goes to 0, then your retarded time should just be like t minus r over c. If you think about the particle just sitting at the origin, that should be the formula for retarded time, which tells us we must choose the minus. So having chosen the minus, we put that into practice over here in the purple formula. And then we're working on calculating the denominator for the Lienard-Wiechert potential. And we do that. We have to plug in that lovely T sub r down here. So, hooray. We replace, I'm just plugging in the r and the r hat. And then in the green step, I replace the retarded time with its solution from the quadratic formula. Thankfully, some stuff cancels. And it just leaves you this lovely root with a 1 over c. And then that brings us to the Lienard-Wiechert potentials for a constant velocity particle starting at the origin with charge q. So, yeah, that's the voltage and the vector potential for a point charge that's moving with constant velocity v. And he writes this constant in terms of like qc mu naught over 4 pi, because he doesn't like to have the epsilon naught c downstairs for some reason. Anyway, so yeah. Okay, that's great. What's the electric and magnetic fields? Oh, yeah. You see what you'd have to do to find E and B from this, don't you? You got to take the gradient of this. Notice this is x, y, z. It has an x and y and a z dependence there. That's got an x, y, z dependence. That's x squared plus y squared plus z squared. There's a t dependence everywhere in this bloody thing. And like down, you take the gradient, minus the gradient of that, and then minus partial a partial t of this. Good night. Like, to actually calculate the electric and magnetic field here, it seems hopeless, doesn't it? And yet, stone cold formulas are given for both of these in the next section somehow. And not just for constant velocity, but for arbitrary velocity and arbitrary acceleration. How does that happen? What happens in the mathematics of the next section to make that stuff come together? I don't know, but I'm hoping to work it out and show it to you Friday. So, yeah. I don't know. It's like what the final section in chapter 10 is maybe the coolest part of the entire book, honestly. I don't know. Like I love it. But anyway, I shut up. See you guys Friday, hopefully.